Okay, good evening. My name is Dr. Phil Crable. I'm a counselor here at SCC and also work in our STEM programs. Thank you all for coming out. Some quick program notes before I do introductions. For those of you that are here, whether you're getting extra credit for the class or you are here in the STEM programs, please make sure you sign in if you haven't already on your way out today. We have some sign-in sheets in the back. So, welcome to the Physics Guest Speaker Series. Or should I say, may the 4th be with you? Yeah. We have a speaker here with us this evening who is kind enough to join us again after last year, coming back for a second time and giving a lecture today from California State University, Fullerton. We can just go ahead and get started right away. Welcome Dr. Jeffrey Lovelace from California State University, Fullerton, Assistant Professor of Physics.
Thank you very much for the invitation. I'm glad to be able to talk to you all today again. I want to tell you a little bit about supercomputers and how we use them to study black holes that are smashing into each other. This is an especially fun time to be talking to you about black holes and gravity because actually this year is 100 years since Einstein first proposed the theory that we still, as far as we know, think accurately describes how the universe behaves and how gravity behaves. So I'll tell you a little bit about that at the end of the talk. I'll be happy to answer as many questions as you might have. Okay. Let me say a little bit about myself first. I'm a professor at Cal State Fullerton in the physics department and also in our Gravitational-wave Physics and Astronomy Center. So this is actually 3 different professors, Josh Smith, Jocelyn Reed, and me, and we each work on different aspects of this kind of new kind of astronomy. Josh is actually going to be here in this room Wednesday at 4 o'clock, and he's going to tell you a lot more about the experiment that I'm showing you in a picture here. So I wanted to make sure that you knew about that. The plan today is I'm going to step back and tell you a little bit about gravity, what gravity is, and how, a little bit of the history. I'll take you on a bit of a quick tour through the history of how we learned about gravity and how we've thought about it. Then I'll tell you about what black holes are. And I'll finish up by talking about some computer simulations of black holes smashing into each other, and I'll show you some of the stuff that's going on and some at Cal State Fullerton and some research opportunities that we have there. Okay, so let me just step back and start trying to get at this question, looking at it through history. What is gravity? So, there were a lot of people who thought a lot about gravity since antiquity, but Galileo gets a lot of the credit. He wasn't the only person who was doing these experiments at the time. He ended up being the most famous, but he did an experiment, and the experiment was to see how does gravity behave near the surface of the Earth. It's something we're all familiar with in everyday life. I mean, if you take something like you take this water bottle or anything near the surface of the Earth and you drop it, it's going to fall. And if you were to go and jump up in the air, you're not going up forever, you're falling back down. But the question is, scientists want to know more than that. We want to know quantitatively, how do things behave? Do heavier things fall faster, or do lighter things fall faster, for instance? So here's an experiment, and I'm going to play a video here in a second. And what they're going to do is they're in this big room, and then here's a famous professor, Brian Cox, standing down here, and he's narrating some show for the BBC. And he's going to do this experiment where they drop some feathers and then they drop something much heavier, this bowling ball here, at the same time. Now, some of you might have had a physics class, some of you might not have had a physics class. This is just an ordinary room, and they're going to drop these from the ceiling. Do you think that one of them is going to fall faster, or do you think they're going to fall at the same time? You think one of them is going to fall faster. Which one's going to fall faster? Yeah, the ball. So let's see if that's what happens.
Galileo's experiment was simple. We took a heavy object and a light one and dropped it at the same time to see which fell.
Okay, so now they're going to redo the experiment. This room they're standing in is actually the world's largest vacuum chamber, so he's going to leave for his own, it's bad for your health to breathe vacuum too much, but he's going to leave, and then they're going to pump all the air out, and then this is what happens in the next one.
Relief.
So they're showing it in slow motion, and here you can see without air, they're both accelerating in exactly the same way. Okay, the video keeps going for a while. So when you could ignore air, the big insight the Galileo experiments had was that objects fall at the same rate. But gravity doesn't just apply on small everyday life scales like this. It also applies out in space. It's what keeps moons going around planets. It's what keeps planets going around stars and stars going around galaxies and the galaxies moving relative to each other. Once you get away from the surface of the Earth, gravity doesn't have this simple behavior. Everything just accelerates the same way. So how does gravity behave? How do we learn about that? This is an image taken by the Hubble telescope. This year on January 24th. And this is cool because it shows 3 of these 4 moons that are now called the Galilean moons. These are the biggest moons of Jupiter. Here's Europa. This one is made of ice and has liquid water underneath the ice, we think. And this is the shadow that it casts from the sun. So it's doing a little eclipse on Jupiter here. And then here's a bigger moon, Callisto, and then here's its shadow. And here's the third one. So there are 4 of these big moons of Jupiter, and this is showing 3 of them. So the question that people had then, once Galileo looked up with his telescope and saw these moons, he saw that they were going around, they weren't just wandering randomly around the sky, they were moving around Jupiter. So here's one of his books, and he drew these little cartoons where he showed the moons at different places at different times, and by seeing how they looked at different times, he could tell they were all going around Jupiter. This is one of the first times we actually saw something like a solar system, something like a bunch of objects going around some heavy object in the middle. And the question was, how do you understand this? Why does this happen? Well, Galileo was excited just to discover them. This is a really neat book. I took this picture myself. This is at the University of Oklahoma, where I went to college. And they have this really neat history of science library. And if you look at this picture, this is Galileo's book talking about these moons that he discovered. This is a copy he gave to someone named Gabriel, I guess. And this is his handwriting. He wrote them a little note and signed it here. So they've got a book there with Galileo with his writing from hundreds of years ago. And so let me just show you a few of the things that he had to say here. This was published in 1610. So this idea, we've known about these moons only since we had a telescope because they're too small to see otherwise. And here, he didn't call them the Galilean moons, he called them the Medicean stars. And why would he do something like that? Well, here's this great quote from Galileo. And he says, "Since it's up to me, the first discoverer, to name these new planets, that I wish in the imitation of great sages who placed the most excellent heroes of that age among the stars to inscribe these with the name of the most serene Grand Duke," which he didn't mention here. He was hoping to get a big research grant. So he wanted to get some money to support his research, and he was very shameless about saying, "Oh, well, I just discovered these brand new things, and we'll name them after you." So he liked that, and it worked, and he actually got the money. But the name didn't catch on. So a little bit later, people were thinking, well, how does gravity cause the moons to keep going around Jupiter? Why don't they just fly off in straight lines? So some of you who have taken a physics class might have seen an equation like this before. The idea is every 2 objects in the universe, with Newton's idea of gravity, pull on each other. And so my 2 hands are attracting each other gravitationally. Any 2 people in the room gravitationally are attracting each other. And how strong that force is depends on how massive you are. These are masses. And so if you multiply each of your masses, say in kilograms together, and divide by how far apart you are squared, that's how far away you are. Now this picture here is Newton's own personal copy of his big book called the Principia, where he first wrote down, among other things, his law of gravity. And here he's like putting some little corrections on there that show up in future editions, but this was his personal copy. And if you translate this, here's an old English translation. This is the first time he really wrote down this idea that the gravitational force is pulling towards the center, towards Jupiter's center. It's pulling the moons towards the center, and it falls off reciprocally with the square, so 1 over the square of how far apart they are. So this theory of gravity is actually a pretty old theory. It was first published in 1687. But even today, this is the theory of gravity that you learn about if you were to take a physics class or an astronomy class. Because it turns out that under almost all conditions you can think of, this theory of gravity turns out to describe how objects pull on each other gravitationally. This explains why and precisely how the moons of Jupiter go around Jupiter, and how the Earth and the planets go around the Sun, and how the Sun goes around the galaxy. So this theory explained pretty much everything that we knew about until 1915 or so, around the turn of the century. Einstein proposed a modification to Newton's idea of gravity. This is his paper in German about the field equations of gravitation. And then this is a handwritten copy of a paper that he wrote to explain it a little bit later. But not everyone was too convinced for a few years that Einstein's new theory was right. He re-envisioned gravity not as forces pulling on each other. So it's not that, that you and I are pulling on each other with a force and that every object is pulling on all the others, but gravity bends space and time. And everyone thought, well, this sounds weird. Why should we believe it? Well, it turns out a few years later there was a solar eclipse. And the one prediction of Einstein's theory that's different from Newton's is that by bending space and time, light can bend. So here's a star that happened to be directly on the line between the sun and the Earth. And it sends out starlight. But the sun's gravity, according to Einstein, should bend that light. And during the eclipse, you should be able to see the star. Because when that light gets bent on Earth, it looks to us like the star is to the side of the sun, because the light got bent around it. So when we see it, we can see the star, even though we shouldn't, aside from space and time being curved. If it weren't, the star would be hidden by the sun during the eclipse. So they went to see if they could see stars like this on the edge of the sun during an eclipse that they knew were actually behind it. And it turns out they could. And here's this headline from the New York Times back then. And they said, stars aren't where they seem to be or calculated to be, but nobody needs to worry about it. And they talked about Einstein said no more than 12 people in the world could comprehend this theory of gravity. And gravity has had this bad reputation that it's really cryptic and hard to understand and hard to learn more about. And part of what I want to tell you about today is that this isn't necessarily true. So this is a picture of a conference that I was at in Poland a couple of years ago, in 2013. And every single one of the people that you see here in the room is an expert who's working on unraveling what Einstein's theory predicted. 100 years after he first wrote down the equations, it turns out they're hard to solve, and when you do solve them, it's hard to understand what it all means. And we're still trying to unravel exactly what this idea means. Einstein himself just didn't really see very far, and some of the theory's most famous conclusions, like black holes, Einstein didn't even believe it. But that's one prediction that his theory made, and that's what I want to talk about now. But even though I told you a little bit about about the history from the 1600s to today, and I only had time to mention a few people, this has always been a really big effort with a lot of scientists trying to find out more, to describe more accurately about how gravity works. Now what I want to tell you about in the next part of the talk is, okay, so how does gravity work? So it turns out that even though Newton's theory is very old, it almost always works. And there's this idea that if you take your mass times my mass and divide by how far apart we are squared, aside from some constant, that's going to be how hard gravity pulls. And you can understand all of the gravitational motion this way. This is fine if gravity is weak and if velocities aren't too big. Now, it turns out that that's true most of the time, but it's not really true for black holes, the kind of case we're going to be talking about today. Gravity can be really strong, ridiculously strong, and things can move really, really fast. And when that happens, then Einstein's theory of gravity is the one we have to use. Most of the time they give the same answer, and Einstein's theory is just a lot harder to calculate with, but with black holes you have to worry about it. So here's how you can think of curved space-time. If space and time are like a pool table, then when there's no gravity, it's like a flat pool table. And unless there's a force acting on the cue ball or something, it just goes in a straight line. But now, Brian Green here is going to use the power of computer graphics to show us what curved space-time looks like. So here he's going to bend the space of the pool table. And now when he hits the cue ball, it still is going to move in the straightest line it can, but because the table is curved, the ball moves in a circular orbit now. So this is what I want you, the kind of thing I want you to picture when you picture gravity. This is why the moon goes around the Earth. The Earth's gravity curves the space and the time around the Earth, and that causes the moon, it's moving in the straightest line it can, but the space and time are curved. Here's another example. Have any of you ever put money into one of these things? So why is it's went into slow motion here, why does the coin, why doesn't it just orbit it forever? Why does it fall in eventually? It's friction. Friction, it's losing energy to friction. And later on, we'll be talking about this idea of how when black holes orbit each other, they can fall in just like the coin falls into the hole here. The two black holes can fall into each other. They're losing energy not to friction, but to some, they're sending energy off as little ripples of gravity that go out across the universe. So, let me tell you a little bit about black holes. They're a little bit like this coin funnel. When you put the coin in the funnel and it falls through the bottom, it's not coming back. You can't get in and pull it out. And similarly, when something falls inside a black hole, if you were to dive inside a black hole, it's bad for your health, partly because you're not coming back. You'd have to go faster than light in order to come back once you fall inside a black hole. The gravity is so strong, the space and time are curved so much that inside its surface, which is called its horizon, nothing can get out. Even light can't get out. Nothing is coming back. So not only would you be stuck, but you wouldn't ever be able to send a radio message or anything to tell anyone about what you were seeing. Now these things exist in the real universe, and they're formed when the biggest stars that there are in the universe, when they die, when they run out of fuel, so they're not able to shine anymore, then what happens to the biggest stars is their gravity will collapse them into black holes. Here's a picture of a black hole. If the black hole isn't rotating, its surface is just a sphere like this. But it's hard to visualize how space is curved. If you have 3 space dimensions and then time, visualizing all that curving is hard. So here I'm taking the black hole at a snapshot in time, and I'm just going to look at one little slice of the black hole right through the equator here. And so this horizon is just a circle, and I'm going to show the space just in the equator here. And then I'm going to use that 3rd dimension to show how it's curved, and it looks kind of like a funnel again. So the idea here is the weaker the curvature of this funnel, the farther away you get from the black hole, the closer the space is to being flat. And so the less you would feel the black hole's gravity. And just like the coin can go around the coin funnel, aside from friction, you can orbit around a black hole. Black holes don't suck. They don't just suck everything right in. You can actually orbit right around in a circle. So let me give you a feel about what black holes are like. So they sort of come in 2 flavors. One kind of black hole is a kind of like star size, kind of like the sun, maybe a few times as massive, maybe 30 times as massive as the sun. There's another kind that might be millions of times the mass of the sun, and they tend to live in the centers of galaxies. Okay, so how big would this be? It turns out, even though the mass is so big, it's squished into a really small size. So here's my office at Cal State Fullerton, and here's where we are at SCC. Now, if one of my students messed up in my lab and made a black hole that was centered right here, and let's say it's going to be a typical size, about 10 times the mass of the sun, I'd be really worried about how any of my students could do it, but I wouldn't put it completely past one of my students' room. Some of you might know him. This is how big the black hole would be. So we'd be in trouble, but it wouldn't even reach to downtown Los Angeles. So this is 10 times the mass of the sun. If you had a black hole that massive, it wouldn't even be the size of all these Southern California city conglomerate things. It wouldn't even reach from here to downtown Los Angeles. If the Earth were squished to be a black hole, this is how big it would be. It'd be less than the size of a golf ball if you squished all that mass down. So black holes are these really extreme objects. They're really massive, and they're also really, really small. Now, how massive a black hole is tells you how big it is. The more mass falls in, black holes can actually grow. They can get bigger. But black holes also have one other property that I want to tell you about. They can rotate. When a black hole rotates, so let me tell you about what happens when a black hole rotates. It sort of swirls the space and time around it like a tornado swirling the air around it. That's how you can picture it. This is another picture if I slice through the middle of the black hole and just use this to show the equator, but then show how the space is curved. The curvature gets stronger as you get closer to the horizon, which is a circle again. But now these arrows are showing that it's sort of swirling space around it. Another thing this cartoon shows is it shows how time is warped. It turns out, as you get close to a massive object, especially a really massive object like a black hole, time flows a lot slower the closer to the center you get. So as you get closer to the black hole's horizon, time starts slowing down. This color is going from purple down to red as time flows slower and slower. Red means it's flowing 1/10 as fast as it would be far away. So what does all this mean? Well, I'll show you an imaginary experiment. Let's say we have a black hole, and let's say it's not spinning, so it's just a sphere. Well, I'm the professor, so somebody's got to write the paper and tell everyone about it. So I'm going to stay out here at a safe distance. But I'm going to take one of my grad students, Evan, and Evan's going to do an experiment for science and dive head-on into the black hole. So as that happens, I would see Evan's wristwatch start ticking slower and slower compared to mine, as he's getting deeper and deeper into the warped time. But otherwise, he would just fall straight in. But now here's what would happen if we didn't do this experiment, but instead found a black hole that's spinning 99% as fast as possible. And sometimes I'll use this Greek letter chi to just say the spin of a black hole between 0, which means it's not spinning, and 1, which means it's as fast as possible. So if it's spinning 99% as fast as possible, then what happens? So I'm still going to stay out here because somebody's got to go get write all the papers and find out what happens. But I'm going to send Evan into the black hole. And this time, even though he dives in head on, this black hole is rotating. It's swirling the space around it so much that he starts getting pulled into rotation. And in fact, inside this little gray region here, but outside the point of no return, where if he falls inside the black sphere, the horizon is not coming back, in this region, he actually is forced to rotate with the black hole. It's impossible to resist it. So a black hole spinning just swirls everything around it into rotation. And these are the two main properties that black holes have. The mass tells you how big it is, and then it can spin slower or faster. Okay. So how do we actually know that any of this is true? Einstein's equations predict all this, but how do we know any of this is true? Well, black holes don't emit any light. If light is emitting from somewhere inside, well, it can't ever get out. So how do you ever know they're there? This is a picture of the stars at the center of our galaxy. We aren't able to focus on them, but you can see how they're moving. And now it's going to zoom in and watch what these stars are doing right here at the very center of the galaxy. There's no light there, but watch what this star does. It whips right around there, and that whipping motion, according to not just general relativity, but also even Newton's law of gravity, that whipping motion can only happen when there's something really, really massive there that this star is orbiting. But it's not emitting any light. We can't see it. And by exactly the timing of how it sweeps around there, we can figure out how massive this invisible thing at the center of the galaxy must be. And it's something like 4 million times as massive as the sun. So there's something 4 million times the mass of the sun, and we can't see anything. And the only thing that we know of in science that could do this is a black hole. Here's another black hole, a much smaller one. This black hole is only 15 times the mass of the sun. And when we look at it, there's some light. So why are we seeing light when it's a black hole? Well, it's just like if you put metal into a fire, it starts heating up and then it starts glowing. As matter falls into a black hole, so there's just some gas from a star that's near the black hole. As it falls in, it heats up as well. As it falls in, it moves faster and faster and heats up and glows. And in this case, it's glowing X-rays. So you can try to look at precisely what this light looks like to see how fast a black hole is spinning. And you can try to look at how objects are orbiting around a black hole to try to figure out how massive it is, like this. But these are both kind of indirect. Especially this idea is really sensitive. It depends on how you think that matter behaves as it's falling in. And that can be really complicated. So what we'd like to be able to do is look at black holes in an entirely new way. Even though they're black and they're invisible, they don't emit any light, it'd be really neat if we could see them directly and not just look at them indirectly, at their effects on matter that is unfortunate enough to get too close to them. So this is a picture of the tool that we can use to learn more about black holes. One black hole by itself it's still pretty much out of luck. It's hard to study it directly. But the thing I want to tell you about now is what happens when two black holes are orbiting each other, and then they lose energy, like the coin going down the funnel, and then crash into each other. This is a new computer simulation of what this would look like if there were two black holes somewhere in our galaxy going around each other, and then they merge. The black hole's gravity is so strong that just like the sun bends the starlight a little bit, so you can see stars during an eclipse, here they're bending light a lot. And you see all this weird lensing going on. The shadows are where the light never makes it back because it ends up going down the black hole's horizon. Eventually the holes spiral together and merge and make one new big black hole. This is brand new. As of a year ago, maybe it's about a year old, this is the first time we've been able to see what something like this would look like, and we have to do it using computer simulations. So how does this work? So there's three different stages that you can think about. But when the black holes orbit each other, at first they're just sort of spiraling together slowly. And as they spiral together, they go faster and faster and faster until they smash into each other. And then they make some really distorted black hole that's sort of dumbbell-shaped. And the vortex, or if you slice through the equator, like I was showing on those other cartoons, it looks complicated. But then the black hole rings and settles down. It settles down to just an ordinary new big black hole. This is a lot like a bell. If you strike a bell with a hammer, the bell deforms, but then it rings and it quiets down. If you zoom out here, so that the black hole's funnels are here, and I'm showing you the curvature of the space, like in these other cartoons, what you see is these little ripples going out. They're just like water ripples going on a pond, except these are waves of gravity shooting out across the universe at the speed of light. When two black holes smash into each other, these are the most violent events you can get anywhere in the universe. When black holes smash into each other, they can convert more energy than a supernova into gravitational waves, these little ripples of gravity. None of the energy goes into light. They're totally invisible, unless there's some matter nearby that gets disturbed a bit, and you can notice that all this energy is going into invisible explosions in the sky, and we want to be able to see them. And to do that, we have to be able to detect these little ripples of curvature, these gravitational waves. So what effect would a gravitational wave have if it were coming through you, this little ripple of curved space and time? If you had a ring of particles like this, and there's a gravitational wave going into the screen, then what it would do is it would curve the space and time around the ring of particles in some back and forth kind of way, so that it would change the distances between them. The distance on a curved path is different from a straight path, and so the effect of gravity is it would make these things wiggle back and forth a little. And then here's what a gravitational wave would look like. If you had a whole bunch of these rings, the wave would just travel through all these particles at the speed of light. So I've slowed it way down so that you can see it. So you can imagine setting up a giant mesh of particles like this and looking for them to start wiggling when a gravitational wave comes through. So here are the gravitational waves coming out across the universe, and then when they get to the Earth, here I'll just show one ring of particles. Imagine the gravitational waves are coming in from you towards the screen. When they do that, then they start wiggling back and forth, all the little particles. But they don't wiggle very much. It's really exaggerated. So anything, like even air, would really mess up this experiment. So just like in that first experiment where we had to evacuate the air to drop the feather and the bowling ball at the same rate, you need vacuum. And vacuum's expensive, so no one's ever built a machine like this. Instead, they just pick the mass up here at the top and the mass over here, and they just have two masses going back and forth. And that's what this is. This is a gigantic vacuum tube. It's a 4 kilometer long tube, and they just pumped all the air out. And there's to a really, really good degree, there's nothing in there, and except the laser light, and the laser light then can travel undisturbed. When a gravitational wave comes by, the mirror down here, and then another one 4 kilometers over here, this way, are going to start wiggling back and forth. When the mirrors wiggle back and forth, what happens? Well, when they wiggle back and forth, this detector has shines lasers off the mirrors so that whenever they wiggle, they'll see something. But they don't wiggle by much. And that's the problem. Even the brightest, loudest gravitational waves we can think of, when these little ripples of gravity get to Earth, they're really faint because the things that produce them, like colliding black holes, are so far away. And when they're that far away, then they're only going to move these mirrors by 10 to the minus 18 meters. Now let me show you how small that is. To the nearest power of 10, we're all about 1 meter tall. If you go 10,000 times smaller than that, that's about how thick a single one of the hairs on you is. And 100 times smaller than that is the distance between two peaks on a light wave that you're looking at. And 10,000 times smaller than that is the size of an atom. And 100,000 times smaller than that is the size of a proton in an atom. And we're measuring distances 1,000 times smaller than that. So this is a really, really delicate experiment. These gravitational wave antennas, you can think of it as an antenna, like trying to pick up a radio station. We're trying to pick up these gravitational waves, and they're so quiet that these antennas have to be built to be exquisitely quiet. So not too much static in them, not too much noise in them. But even with the best detectors that we can come up with, it's going to be really hard to hear these gravitational waves. It turns out that when two black holes smash into each other, the frequency of the ripples that they send out is actually the same frequency that we can hear. So if you plug your gravitational wave antenna into speakers, like a stereo antenna, then you can actually hear something. This is a simulation one of my students at Cal State Fullerton did of a gravitational wave from two black holes colliding with each other. Here I'm showing you the wave. This is how much the mirrors would be moving back and forth in some sense. But basically, if you plug this into speakers, this would be a sound wave. And I'm going to play a sound and see if you can hear what it sounds like. The sound was cutting in and out a little, so let me see if it sounds okay. Okay, so the sound's cutting out a little bit, so it shouldn't get quieter at the beginning. It just sort of chirps like whoop. Okay, so that part at the end is what this gravitational wave would sound like. Now, I'm going to play some simulated noise from even our best possible detectors and see if you can hear a sound like that in there. Yeah, I couldn't hear it that time. I'll try it one more time. I think my microphone might have been causing trouble. So there's a gravitational wave. Now listen, it'll be really quiet. Okay, did any of you hear a little chirping sound in there? Yeah. Okay, some of you could hear it. It's really hard to hear. This is the whole problem of detecting gravitational waves. It's really hard to hear. So there's two things you can do about it. You can build a better antenna, or you can train the experiments to know what they're listening for. If you're at a crowded party and you're trying to hear what someone's talking about on the other side of the room, it's really hard to hear what they're talking about. But if you hear someone call your name over there, you can turn around and you hear it. And the reason is you've trained your whole life to recognize your name, especially if the voice is someone you know, like maybe someone from your family. Then it's easier to recognize that in the noisy room. And similarly, we want to train the experiment so they know what the gravitational waves will sound like. So here's, this means we have to solve Einstein's equations to describe black holes. Now I've already told you about some black holes. Single black holes by themselves, here's how we've learned how to solve them. So I'm picking up the trail of this story through history a little bit. Einstein's theory came out in 1915, the equations of relativity, and 1 year later, Carl Schwarzschild solved them. He's a cool guy. He was actually a soldier fighting in World War I at the time, and I guess on break or something, he managed to find out about this paper, and he managed to solve the equations for the first time. And it took a while to unravel what his solution actually meant, but it turns out he discovered how single black holes behave if they're not spinning. Now, here's a guy named Roy Kerr. It took until the 60s for someone to discover how a black hole behaves if it's spinning, swirling space and time around it. My boss at the place I used to work for, Cal State Fullerton, once interviewed and met Roy Kerr, and he described him now. He's still alive, but he's a bit of a curmudgeon. And he's, he had this one big paper, and he has opinions about a lot of things. And that's stuff. I've never met him, but that's what he's like. So what we've been doing so far is talking about solving single black holes. A single black hole is just going to sit there by itself. It's just going to sit still. It'll be spinning at some steady rate maybe, but otherwise nothing really happens to it. And that's a lot like looking at a calm surface of a lake. If you want to know how the water's going to move, it's pretty easy to describe. And maybe it gets disturbed a little, like you drop a rock in it, or maybe the black hole gets disturbed a little, because someone like Evan falls into it. But the black hole itself doesn't change too much. It just wiggles a little bit and then settles back down. Well, two black holes crashing into each other is a lot more like this. Imagine trying to solve how the water is going to behave when there's all this wind blowing and all these waves going around. It turns out, and actually for kind of similar reasons, this is hard to solve the same way. This is why we have to use computers to predict like what the weather's going to do. Similarly, you have to use big computers in order to solve these equations because they're so complicated, no one knows how to do it any other way. When you have two black holes that are spinning around different axes and they orbit each other and they come together and smash into each other. Now, we first tried to do this, not me, I was not bored, maybe very close to that. But it took until 2005, just 10 years ago. So relativity came out 100 years ago. And Einstein first proposed it. But only 10 years ago was the first computer solution of two black holes. I happened to be a grad student at the time, and Frank was a postdoc in the same group. And he came in to the group meeting one day and said, hey, I have this movie I want to show you. And we all saw for the first time what it would look like for two black holes spinning around each other to smash into each other and merge into one new big black hole. And that's what the paper looked like that we wrote. And since then, though, black holes come in all different sizes, and they come in they can spin around different axes at different rates. So it's not like there's just one solution that describes them all. You have to solve the equation over and over again for all the different kinds of black holes, so that we can predict all the different possibilities of what the experiments like the antenna that I showed you earlier might actually be able to hear. This is a conference at Cal State Fullerton where we had about 50 people from all around the world coming to talk about how to use computers to model gravitational waves, and then how to use those to help the detectors hear as many of these little ripples of curved space-time from black holes smashing into each other and other things as they possibly could. So this is a really big effort from a lot of different research groups, and the research groups at Cal State Fullerton are playing a part in that big program. Okay, so let me tell you a little bit about what these computer simulations are like. So we want to predict exactly what those waves are going to sound like, that what sound, so that we can help the experiments find as many of them as we can within the static. And also, once they do find them, so we can try to find out, okay, what kinds of black holes created it? So here is the kind of computer that you would use to do a simulation like this. This is a computer called Orca. This was Dr. Smith's idea. He wanted to have sort of an Orange County or ocean kind of name to it. So this is the Orange County Relativity Cluster for Astronomy. This computer has 600 cores. My laptop has 2, so this is like 300 laptops all networked together, and it's got over a terabyte of RAM and a giant disk. And when you use this thing, it can still take months to do just one simulation of the last fraction of a second of the black holes spiraling each other and smashing into each other. So these are really, really computationally expensive, and we need to do a lot of them in order to find out how all the different kinds of black holes smashing into each other sound a little different. Here's a movie of a computer simulation. The top is showing the black hole surfaces orbiting each other, and here I'm showing you the curved space and time. And then they go faster and faster, and I'm going to pause it here just after they've merged into a big black hole, and then that big black hole sort of rings like a bell down to some new relaxed final thing. So I'll play that for you one more time. Oops. Okay, so here the black holes are going around each other. The red the time is flowing more slowly because the time is so warped. And down here, this is what the wave of the gravitational waves would look like if you were to put it on the screen. And here they've merged, and then this thing settles back down into some brand new black hole. This was the first simulation done by the research collaboration I'm a part of. This was done in 2009. Since then, we've done more. Here's why. This is one kind of black hole collision. The black holes have the same masses, and they're spinning a little bit, and these arrows are the axis. So you take your right thumb and point it on that axis, then your right fingers are going to tell you the way the black hole's spinning. Here's another case where the spin axes are in random directions, and one black hole is bigger than the other. These two different cases create black gravitational waves, the ripples that go out across the universe, that are totally different from each other. So in order to prepare the detectors for all the possible cases, we have to do all these different kinds of simulations. Here's a movie of the black hole's horizons here. So the horizons are tracing out their orbits as they go around each other. And now this hole is going to come in, and it's just going to sort of go sploosh into the big black hole. I can slow that down for you a little bit. So here they go. And now briefly, we've got this very weird shaped black hole horizon that's got this little tongue coming out of it at the front. But then it really quickly sort of rings back down. This is a movie of all the cases that we've been able to do so far. This was made by Arun Khan. He's a student in my research group who was a student at Santiago Canyon College. I'm going to start playing the movie. This is showing things like the relative sizes of the horizons, tell you how massive the black holes are, and the little lines are the arrows showing you the axis they're spinning around. Some of our simulations have the orbits stay in a plane, like the Earth's orbit around the sun, and those orbits are white. But sometimes the orbits wander around in some complicated pattern, and those orbits are green. As the black holes get more and more yellow, they're spinning faster and faster. And now they've all merged, and this gives you an overview of the kinds of black holes that get created. There are a lot more black holes spinning pretty fast, orange and yellow, than some that are red. It's harder to get a black hole that's spinning slower than it is to get a black hole that's spinning faster, as it turns out. So cartoons like this are something that the students in my research group like to make, and the reason is these simulations spew out a huge amount of data. They can, one simulation might be a terabyte of data, so that's something like a, maybe like 100 movies or something like that, if you want to think how big they are. But all these numbers don't mean anything, and we need to turn them into something visual so we know what it's all about. So here are some pictures of some of the students at Cal State Fullerton and some of the things that they're up to in my research group. So here are a couple of students working on a computer. This is just a regular computer that's connected to the big supercomputer. We recently got a grant from the National Science Foundation to make our computer bigger. And so here's one of my students, Misha Shari, and a couple other students. Sean, these students work for Dr. Reed. And here are a few of my students at a conference we went to recently. We got to meet Kip Thorne. He's done a lot of groundbreaking work on gravity. And if any of you have seen the movie Interstellar, then his ideas and calculations were behind a lot of the effects that you saw in the black hole and wormhole in that movie. So these are some of the things that we worked on. What I want to tell you about to sort of wrap up the talk today is just one recent project that's been going on here. It turns out in the universe we see some black holes that are spinning almost as fast as possible. I want to tell you a little bit more about what that means. So if you take the spin of a black hole, multiply that by 8 pi, and divide it by the surface area of the black hole's horizon, the black hole's surface, that number should always be less than 1. This is called the spin limit of a black hole. If a black hole by itself were to spin faster than that, you can use Einstein's equations to show that the centrifugal forces would tear the black hole apart. Just like if you're on a merry-go-round and spinning and you feel yourself pushed towards the outside, if a black hole were to spin too fast, those kinds of forces would be so strong that the black hole's horizon would be obliterated. But this is only known for single black holes by themselves. The question that we wanted to look at was, when two black holes smash into each other and you get these weird horizons, like maybe a tongue-shaped horizon like the one I showed you a little bit ago, what happens? Does it still obey this kind of a limit, or can you get a black hole that's briefly spinning faster than that? So this is a question that our simulations will let us answer. We're doing the simulations mostly to help the gravitational-wave experiment that Dr. Smith is going to tell you more about on Wednesday. But along the way, they also tell us something new about what Einstein's theory predicts for how black holes behave. So do these colliding black holes obey the spin limit? So this is a paper that recently came out. These are a couple of the authors, Misha Shari, Nick Demos, Rosa Kateri. These are a couple of co-authors on the paper. All the students who are highlighted here either are current or former students in my research group at Cal State Fullerton. Now this paper is nothing like the other papers that I was showing you from really famous people like Galileo and Einstein and things like that. But even though it's a much smaller piece of the puzzle, it still is telling us a little bit more of the story, a little bit more that we didn't know before about how black holes behave. And when you go to a university, whether it's Cal State Fullerton or some other university, and do a research project, that's the kind of thing that you'll be doing. You'll be contributing in some small, maybe small, but meaningful way to learn something no one ever knew before about something. In this case, we're learning something about how black holes behave. And I want to tell you just a little bit of what we learned. This is a picture of one of the horizons. They don't get quite so distorted as the one I showed you earlier. This is as distorted as they get. We had two black holes that were the same size, but they were spinning really fast. And when they crashed into each other, the new black hole horizon looked like this. It turns out, right at a time like this, right after the two black holes had merged and made this sort of distorted black hole horizon like this, that's when they tend to be spinning the fastest. And what we did is we plotted how fast they were spinning initially to how fast they're spinning at the end. And this is what this looks like. And it turns out that for a single black hole, this can never be bigger than 1. And for our black holes, for the fastest spinning case we did, we got a final spin of 99.99% as fast as possible. But this limit turned out to still hold, even though there's nothing that anyone knows about to say why that should be the case. We're just exploring what Einstein's equations predict by using computer simulations. But no one's actually been able to solve them by hand and show and prove that this has to be true. This is just what we happen to find. So this is the kind of thing that you can participate in. You can not only help the experiments see some new things in the universe, like colliding black holes, but you can learn something new about how black holes behave. So the students did things like they ran some of the simulations. They helped make graphs like this of the data. Sometimes the simulations don't spew out exactly the data you want, and so you have to like reload them from a save state. Just like if you're playing a video game, you have to reload from a save state. You have to go back and rerun them and save some more data. And a lot of this takes time. You have to use these big computers. Usually you have to do it with a command line. There's not always a nice pointing interface for it. But the reward is you can learn something new about how black holes work. So the last thing I wanted to tell you about was a student who came through the STEM² program. The STEM² program here is this really, really wonderful initiative from the Department of Education. And it's a big opportunity for students from community colleges, including Santiago Canyon College, to spend a summer at universities like at Cal State Fullerton doing research. Maroon came to my research group from Santiago Canyon College as a student and had so much fun that even though he's not even a physics major, he decided to transfer to Cal State Fullerton so he could keep doing the research in my group while he pursues his degree in electrical engineering. Recently, Haroon sent into a poster contest and won, and out of 500 people who applied, Haroon was one of 60 who was accepted to this program. Haroon and I got to go to Washington, D.C. for a day. Here's us in front of the Capitol. And the idea was we were supposed to tell our members of Congress why science is so cool and so important. So, you know, I'm used to talking in classrooms, but talking to people in Congress was a little different. So this is actually a picture of the representative of Cal State Fullerton District, Ed Royce, chatting with Haroon about, and here he wrote a little post. Now Haroon's told him all that he came from Santiago Canyon College, but he just posted that Haroon went to Cal State Fullerton, where Ed Royce went. He transferred from Santiago Canyon College, and then he came by and talked about gravitational waves and black holes snapping into each other. This is a picture that Haroon made that's on his poster that's showing how the light gets bent. Like in that movie I showed you earlier, it's two black holes that go around each other. And this picture is new because the two black holes are spinning almost as fast as possible. And so this is the first simulated snapshot of what this would look like that anybody's ever seen before. So I wanted to show you this to finish up, just to give you an idea of the kinds of things that you can do and the kinds of adventures you can have. You'll not only be learning some new things about how the universe works, but you can also help talk to people, people in the community, and in this case, people in government, just tell them about science and why, and what you're learning, and why it's cool, and why it's important to invest in it. Haroon plans ultimate goal is to go to NASA JPL and be a space engineer. And research like this doesn't mean that you're committing to a career of working with black holes on computers, although that's fun if that's what you want to do. But the kinds of things that you learn here are useful, even if you want to go into some other field of science or engineering. So that's pretty much what I wanted to tell you about today. A little bit of history. 100 years after Einstein first proposed the theory of relativity, we're still unraveling everything that it means. The equations are hard to solve, and in most cases we only know how to solve them with these computer simulations. That's the only way we can find out what colliding black holes actually look like and how they behave and what the waves of gravity that they send across the universe sound like. These simulations are going to help us learn and see the universe in a whole new way. We're not just seeing a different color of light, like we saw all kinds of new things when we first looked at the sky in X-rays, when we'd only ever seen it in like visible light before. But it's a whole new spectrum of light, and we're going to learn about all kinds of new things that don't emit light at all sometimes, like colliding black holes. So the research at Cal State Fullerton is going to play a role in this big international effort to make this kind of thing happen. So I wanted to leave you by just telling you that, and not just at Cal State Fullerton, but if you decide to transfer and go for a 4-year degree, seek out some research opportunities. See if you can find out a little